Hello everyone and welcome to our calculus notes for 6.3. Today we're talking about finding volumes of rotational solids using the shell method. So the shell method uses rectangles that are parallel to the axis of rotation rather than perpendicular to it. So what we're going to try to do is take this area right in here and rotate it around this axis right here, so a vertical axis. And so what we get now is we're going to take a rectangle that is parallel to the axis of rotation right here, and then we're actually going to rotate that all the way around. And you can see that it creates sort of a shell around that axis. And you can see if we divide this up into many rectangles, then we get many shells here, and when we rotate all of these here, we're going to get basically our volume of the entire solid. Now this formula is going to go off of the basic formula for circumference, which is 2 pi r. So basically we need to find the area of this rectangle and then multiply it by its circumference, and then we're going to add them all up. And so that's where integration comes into play here. Alright, so let's first talk about revolving around a horizontal axis of revolution. So here's your formula. We're going to get v equals 2 pi times the definite integral from c to d of p of y times h of y times dy, or with respect to y. So let's see what this really means. So if I draw a horizontal axis of rotation, okay, so we want to rotate around this axis, and let me draw the plane region that I'm going to be rotating. Now let's identify what each of these things are. Well, first off, the 2 pi is just because of the actual circumference formula, which is 2 pi r. So first off, let's draw our representative rectangle that is parallel to the axis of rotation. Okay, so you'll notice here that it's parallel right there. So the first thing we need to identify is p of y, which in this case is going to be the distance from the rectangle to the axis of rotation. So there's your p of y. Next we need to find h of y. And h of y is actually going to be the height of the rectangle. And then dy is going to be the width of the rectangle right here. We can call this delta y or dy. And that's just the width of the rectangle. Next we have our limits of integration, and if all of these are y's, we basically want the y values. So we want the y value here from c up to here, which would be d. Okay, so that is for a horizontal axis of revolution. Next, let's talk about a vertical axis of revolution. Here the volume is going to equal 2 pi times the definite integral from a to b, now of p of x times h of x with respect to x. So here's a vertical axis of revolution. And here could be the plane region that we're going to rotate around this one. So the first thing we do is draw our representative rectangle parallel to the axis of rotation. Then we want to identify p of x, which is going to be the distance from the axis of rotation to our rectangle. Then we identify h of x, which is going to be the height of our representative rectangle. And then dx is going to be the width of the rectangle. So here we have dx, which is also delta x. And then for the limits of integration here, since everything's in terms of x, we basically want the x values here and here. So this would go from a to b, and those would be x values. All right, let's see if we can make this a little more simple. Now, one of the keys in all this is to use a representative radius which extends from one edge of the region to the opposite edge. And both the formulas for horizontal axis of revolution and vertical axis of revolution can be summed up in this formula right here. So the volume is going to be 2 pi times the definite integral from a to b of the radius times the altitude times the thickness. So here you can see the 2 pi r, which would give us circumference. The altitude is just the height of that rectangle times the thickness of the rectangle. And notice this right here is going to give you the area of the rectangle. Okay, so we can see it's going to be the circumference times the area. And when we integrate it, it basically adds up all of the shells from a specific A to a specific B. So the easy way to remember this is this formula right here. So volume, using the shell method, is just going to be 2 pi rat, 2 pi rat, with radius, altitude, and thickness. So let's go back up and see if we can't identify the radius, altitude, and thickness in all of these. Okay, so the radius is always going to be the distance from the axis of revolution to the rectangle. So P of y is going to be our radius. And P of x is also that radius. Now the altitude is going to be the height of the rectangle. So h of y is our altitude, and h of x is the altitude. And then the thickness is the thickness of that rectangle, or the width of the rectangle. And so it's always going to be delta y, or delta x. So either way now, we can just use this one formula when finding the volume using the shell method. So let's give it a try. Okay, so it says find the volume of the region bounded by y equals x minus x cubed, which is right here, y equals 0, which is right here, and we're going to revolve this about the y-axis, which is right here. Okay, so if we're going to revolve this, we can draw our picture here. We'd have a mirror image, right? And then all of this would get kind of circled around here. Okay, and we'd also have this empty space in here. So the first thing we want to do is draw a representative rectangle. Okay, and we need to find the radius, which always goes from the axis of revolution over to that rectangle. And so in this case, our radius is simply going to be the x value at the rectangle. We also need to find the altitude, which goes from here to here. And the altitude here is going to be the height of that rectangle. And in thinking about this, it just goes from y equals 0 up to the function. So in this case, it just goes to f of x, and this is just going to be x minus x cubed. And then the thickness is right here. This is just going to be delta x. And the last thing we need to find is our limits of integration. So you can see we're going from here, x equals 0, all the way up to here, and where that intersects is x equals 1. Okay, so you can just set this equal x minus x cubed. Where does that equal 0? Because that's where the two functions intersect. And if we factor this, we're going to get x times 1 minus x squared, which also equals x times 1 minus x times 1 plus x, where that equals 0 would either be at 0, 1, or negative 1, and so we can see the 1 right there. Okay, so let's go ahead and find the volume now. So the volume is going to be 2 pi times the definite integral from 0 to 1 of rat, R-A-T. So R is x, A is x minus x cubed, and then t is just dx. And then using your calculator to evaluate this, we get 4 pi over 15. So essentially do everything except don't put the pi in your calculator, and then we can approximate this, and we get about 0.838 cubic units. And I just want to talk briefly about why the shell method is important. Well, you'll notice here we could have used the washer method. We would have had to take horizontal rectangles. And what that would mean is that all my functions would have had to been functions of y instead of functions of x. So I would have had to resolve so that I could find these lengths right here. So it's much easier if we can just leave them as functions of x. So in this case, the shell method is preferable. Alright, in example 2, we have the line x equals e to the negative y squared, which is right here. And notice that that is a function of y, actually. And then we also have the line y equals 0, which is right here. The line y equals 1, which is up here. And the line x equals 0, which is right here. So you can see the area that we're going to be revolving is right here. And so let's go ahead and revolve that. Okay, just like that. Alright, and we're going to be revolving this about the x-axis, which is right here. So for this, we want to create a rectangle that is parallel to the x-axis. So here's our rectangle. We need to identify the r value. It's going to be from here to here. So r is just going to equal y, because notice that is the height. So the distance from the x-axis to the rectangle is just y. We also need the altitude of our function, which is the distance from here to here, or the height of that rectangle. And notice that it is the distance from 0 to our function. And because this is a function of y, we're just going to leave it as e to the negative y squared. And then our thickness is going to be delta y. So it's important to note here that when we're going around a horizontal axis of rotation, our radius is going to be in terms of y, our altitude is going to be in terms of y, and our thickness will also be in terms of y. And now when we find our limits of integration, we also have to realize that we're also going to want y values. So basically, if we were going to trace this rectangle and slide it, okay, over the entire shaded region, our limits of integration are going to go from y equals 0 all the way up to y equals 1. Okay, so our volume here is going to be 2 pi, because we're using the shell method, times the definite integral from 0 to 1 of rat. So our radius is y, our altitude is e to the negative y squared, and then our thickness will be just dy. And if we approximate this in our calculator, we get about 1.986 cubic units. Okay, so that's an example there where we're going around a horizontal axis, and so we do want our function in terms of y, and you can see that all of this is going to be y's, including our limits of integration. All right, I want you to try number 3 on your own. Go ahead and pause the video, and when you're done, come on back to check your work. All right, welcome back. Go ahead and check your work here. Check your rectangle, your radius, your altitude, your thickness, and that you actually found the volume using this integration formula, and should have gotten about 4.712 cubic inches. All right, let's move on. Now I want to show you this example because now we're going about a line x equals 2, and so it always gets a little more complicated when the axis of revolution is not the x or the y axis. So we want to revolve x cubed plus x plus 1, which is right here. Let's see, y equals 1, which is here, and x equals 1, which is here. So we want to revolve this area around this axis, and so it would mirror on the other side. And you can see our representative rectangle here. And if this were mirrored, it would be over here, and then you can see the shell that's also getting revolved. And so let's just identify a couple things. First thing is our radius. And so we need the distance from here to here. And this is where a segment addition postulate is going to come into play. So we know that this entire distance from here to here equals 2. And we also know the distance from here to here is just going to equal x, right? Because you could trace that down and it would go to any x value on the axis there. So if we're looking for this radius here, r is going to equal 2 minus x. All right, and that is one of the trickier parts, finding the radius when the axis of revolution is not on the axis. Okay, so now we have our radius. I'm going to clean this out so we can see. So next we want to find the altitude or the height of this rectangle right here. Okay, well we know that this height is our function, which was x cubed plus x plus 1. And that is going to be the height all the way down to the x-axis. Now we also know that this distance from here to here equals 1. So if we just want to find the actual altitude here, it's going to equal the function x cubed plus x plus 1 minus the 1 right here. And so it's actually just x cubed plus x. Okay, so that is our altitude right there. And then our thickness is just going to be delta x. Okay, now we have all of our pieces. We have our radius, our altitude, and our thickness. And the last thing we need here are limits of integration. So we just think if we slid this rectangle, okay, all the way this way and then all the way this way, we're actually going to go from an x value of 0 to an x value of 1. So those are our limits of integration there. And so our volume is going to be 2 pi times the definite integral from 0 to 1 of our radius, 2 minus x, times the altitude, which is x cubed plus x, times our thickness, which is just going to be dx. When you calculate this, leaving out the pi, you get 29 over 15, so it's 29 pi over 15, which is approximately 6.074 cubic units. Okay, so very important to draw your picture so that you can actually find the radius, and you may have to get creative, use some subtraction, and then also find your altitude right here. All right, I do want you to try number 5 on your own. Go ahead and pause the video and then come on back when you're done to check your work. All right, welcome back. So you should have drawn this rectangle right here, found that your radius was 3 minus x, and then your altitude is actually the distance between your two curves right here, and so you just subtract the two curves. So we got x plus 2 minus x squared, and then your thickness was just dx, and so here was your volume formula, and you should have gotten approximately 70.686 cubic units. Alright, so that is finding volumes of revolutions using the shell method. Thanks for watching.